Okay, with target 10.3, you need to be able to explain a little bit about the EM spectrum and its different components. Now, why do we have to study the EM spectrum? Let's review. In order to understand how atoms react, you need to understand that they have electrons, and it's those electrons that do the work. So we need to understand electrons. So can we understand electrons? It's really hard. Electrons are very strange. Why are they strange? Because aren't they just particles? Can't you apply Newtonian physics? No. Yes, they are particles, but in some ways they act more like energy than they do like particles. Actually, in some ways, electrons act more like light. So, we have to study light. And that's what we're at right now. We need to understand light. You see, light, like electrons, have a dual nature. They are energy, but they're energy that are also made up of particles. If you don't believe me, then ask your parents if it'd be all right to put a fork inside the microwave. They'll tell you no, because a piece of metal can convert the light particles into electricity, which is not a good thing. Okay? It'll destroy your microwave. Please do not put a fork in your microwave. All right? But that does prove that light is made up of particles. So, what else can we say about light? Light comes in various flavors. The EM spectrum describes for us all the different flavors of light. Yesterday we talked about the difference between Panama City and Myrtle Beach. Well, we can use the same illustration. Over here on the left side of the visible light, this is the only flavors of light that we can see. Roy G. Biv. Our eyes can see those lights. In order to see the other types of lights, we need special instruments that can convert those lights into into a light that we can see. Okay? Anything to the left of visible light, what we have are waves that are really close together. So they're wavelength, and wavelength is symbolized by an upside down Y. It's a Greek letter. Their wavelength is very small, which means you can fit a bunch of waves in a 1 second period of time, so the frequency is very high. Using Myrtle Beach as an example, what does that tell you? The energy is very high. This is dangerous, dangerous stuff. Okay? On the other side of visible light, we have flavors of light whose distance between the waves are very big. How many waves can you place in a given second? Not that many. You can't fit that many waves, so the frequency is low. We're talking Panama City. What's the danger like? Low. Energy is very low. So these are low energy flavors. These are high energy flavors. It's kind of like the difference between being hit with a bullet and being hit with a Nerf ball. You fire that Nerf ball fast enough, it could do some damage. Chances are it's not going to kill you. Fire a bullet at the same speed, it's going to penetrate you. Right? So, this is called ionizing radiation. Why? Because these teeny tiny little bullets can penetrate into your skin and knock out electrons from your atoms. Well, remember what we talked about yesterday. It's the electrons that give you personality. So if you lose an electron and become an ion, then your personality changes. That's when you change atoms in proteins into different proteins. That's where you could alter things. That's where you could also become cancerous. Ionizing radiation is like being hit with teeny tiny little bullets. It's dangerous. If you ever go into a room and this symbol is in the room, that's the symbol, the universal symbol. Everyone in the whole world should recognize that as a room where you have ionizing radiation being emitted, and it's dangerous. Anything on this side, you won't have that symbol because the waves are far enough apart that they may not be able to penetrate. They may be able to penetrate a little bit into your skin, but not very far. Infrared, that's what you guys use on these remotes, these clicker quizzes. You're beaming infrared radiation at me. Microwaves, microwave ovens, cell phones. The cell companies have assigned this range for cell phones, frequencies. Is it all on the radio side? No. Some of it is on the microwave side. What does that mean? We'll talk about it. And radio waves could be many hundreds of feet apart. Okay? So, let's answer some basic questions. Which part represents the highest energy? Left or right? That's right. Gamma, X-rays, ultraviolet. By the way, some of the sun's ultraviolet does go through our atmosphere and hits us. That's how you guys get sunburns. Sunburns are not cute, folks. Sunburns are evidence of cellular damage. So the next time you're out in the sun, you get the nice, cute little rosy cheeks. That means that millions of your skin cells have been damaged or killed, and your body is opening up the subcutaneous layers and allowing blood to flow in order to repair the damage. That means you've just increased the chances of you getting skin cancer sometime in the future. Don't do it. SPF 50 or higher. X-rays you're familiar with because the little lady comes and aims the machine at you, then the lady disappears and goes to the other side of the building. That ought to tell you something. And then gamma rays, of course, caused David Bruce Banner to be converted into the Incredible Hulk, which doesn't make any sense because if he did receive a lot of gamma radiation, it should have killed him, not turned him into a big, giant, hulking green thing. Which part represents the highest frequency? Left or right? Which part represents the lowest energy? Which part represents the longest wavelength? Yeah. Which type is considered radiation? No. Both. All of it is radiation. Electromagnetic radiation. Not all radiation is bad. Only some. Only when the frequencies get to be high enough. Which parts are ionizing? Huh. Which parts are non-ionizing? Okay, so you got it. Good. How do microwaves work? This guy is super.
This microwave oven is a truly remarkable feat of engineering. The rapid heating that makes microwaves popular is made possible by power provided from this vacuum tube. Now, if you picture a vacuum tube at all, it's likely in a radio like this. Inevitably, tiny transistors and microchips replace clunky vacuum tubes, but it's too soon to relegate them to the museum. Microchips can't easily replace tubes for producing power, for example, in heating food. Now, a microwave contains three main components. A vacuum tube called a magnetron. It generates the energy that heats food. A waveguide hidden in the wall to direct that energy to the food, and a chamber to hold the food and safely contain the microwave radiation. In principle, a microwave oven heats no differently than any other type of heat transfer. At a molecular level, heat is a transfer of energy that results in increased motion of the molecules in a substance. Since we aren't quantum-sized, we observe this increase in motion as a rise in temperature. In a traditional oven or stove, we heat food by placing a pan on a burner, or in the oven where the walls radiate heat, which cooks the outside of the food. The insides cook when heat transfers from the surface of the food to its interior. In contrast, energy from the magnetron penetrates into the food, which means the whole mass of the food can be cooked simultaneously. How does it do this? Well, our food is filled with water, which is positively charged at one end and negative at the other. To give these molecules more energy, we expose it to electromagnetic waves that emanate from the tube. By definition, the waves have the electrical and magnetic fields that change direction rapidly. For this oven, the direction of the fields changed 2.45.
Okay, so water is the key to the whole thing. A microwave won't heat diddly if you don't have water or some other polar substance. But water is the ultimate, because water is found in most foods. Except if you use macaroni, like dry macaroni, you put it in a microwave, what happens? Nothing, no. Dry, like dry, uncooked.
Well, yeah, my sister did that and it kind of, I destroyed the microwave with it.
Well, in theory, it really should not have done anything because it didn't have any water. There must have been some water in there. Maybe it had absorbed a little bit of water. Okay? In order for it to heat up, it has to have water. Water's polar. So what happens is that 2.45 billion times a second, that's how you're going to make water rotate. 2.4 billion times a second. Doing that many times a second, do you think it's going to produce some friction? Yeah. So a microwave oven will not cook from the inside out. It'll just cook all the way through. Wherever those waves hit water, that's where it's cooking. But how come some of it is cold and some of it is... Let him explain that to you.
Billion times per second. Water will try to align with the radiation's electric field. The changing field rocks the water molecules back and forth rapidly, and molecular friction from this creates heat as the motion disrupts the hydrogen bonds between neighboring water molecules. Now, you can get an idea of the wavelength of the energy emitted from the magnetron using cheese. Now, you can see on here sections where the cheese is completely melted.
So why are some sections melted and some are not? I know. What do you think? It's the waves. The waves are going through the microwave like this. So wherever it hits the cheese, that's where it will heat up the cheese. That's why you have the little turntable, so that as much of the food is exposed to the wave as possible. Now you can tell how far away the waves are by looking at the cheese. You can actually measure the difference between the melted and the non-melted in order to find the wavelength of the waves. Yes?
Would it be possible to decrease the distance between each wave in the microwave?
Well, then you would have to change the frequency in which you're...
I'm just wondering if it's possible.
And other sections where it's completely unheated. The oven's metal walls only reflect waves of a length that fits inside the oven. This standing wave causes hot and cold spots inside the oven. The three-dimensional pattern of waves is difficult to predict, but the principle can be seen by looking at the waves in a single dimension. The peaks and valleys in the wave represent the greatest energy of the wave. Well, the nodes here correspond to the cold spots inside the chamber. If I measure the distance between melted cheese spots, I find about 2.5 inches. That would be half the wavelength, the distance between nodes, and is pretty close to the actual wavelength of microwave radiation used. Using that wavelength, I can estimate the microwave radiation's frequency. The frequency is related to the wavelength by the speed of light. I get an answer that only has a 4 or 5...
Look at that. And that number right there is the number that's going to be on your instruction manual. You never thought, so who cares how many gigahertz? Well, that gigahertz refers to the frequency. That tells you how far apart those waves are. Get a higher gigahertz and the waves are closer. All right, any questions about microwave ovens? So the question is, really, what you're interested in is if microwave radiation causes water molecules to spin in place, well, what if our cell phones are using microwave radiation as well? Could that be causing any damage? Most scientists will say no. But some scientists are saying yes. What they're looking at is a higher incidence of strange cancers that we have here in the Western world, that the third world countries that don't have as prevalent a cell phone industry as we do don't have. Okay? Like brain cancer. Could it be something other than cell phones? Yes. It could be our diet. It could be other things. Okay? But as it is, Popular Science wrote a really interesting article that I read, and they said, okay, chances are it's not adversely affecting you, but if it is, then the best bet to do is to keep this antenna as far away from your skin as possible. Okay? That means the worst thing you can do is talk on the phone, because you've got the antenna pressed up against the side of your head. Okay, what they're finding is the incidence of brain cancer being more on one side of the head than others. And they're thinking, okay, so according to Popular Science, what are the safer ways in which for you to communicate? Actually, what you want to use when you release and absorb the smallest amount of microwave is when you are texting. Okay, so the next time you're driving and your parents want you to communicate, well then text while you're driving. No, don't do that. I'm just kidding. Stop the car, then text. Okay, if you can't text, then what other way can you communicate and yet keep the antenna away from you? Yes, what? Speakerphone, yeah, put your parents on the speakerphone. What if you can't use a speakerphone? Okay, Bluetooth scares me because Bluetooth is still using the microwaves and sending it straight into your ear. Okay, the hands-free device, this would work as well, because here what you're doing is you're converting into electricity, an electrical impulse. All right, but the one thing you don't want to do is, and boys, all right, so how do cell phones work?
Cell phones. Millions and millions of people use them. With a cell phone, you can talk to anyone on the planet from right where you are. The cellular phone has come a long way in today's society, from the pager, to the first flip phones, to the more advanced, and to the extremely high-tech. Question is, how do cell phones work? It's simple. Cell phones are actually radios. Extremely advanced radios, but a radio nonetheless. The telephone was invented by Alexander Graham Bell in 1876. Wireless communication can trace its roots to the invention of the radio by Nikola Tesla in the 1880s. To understand the sophistication of a cell phone, let's compare it to the walkie-talkie. Walkie-talkies are half-duplex devices. That's when two people communicating use the same frequency, so only one person can talk at a time. A cell phone is a full duplex device. That means you can use one frequency for talking and a second frequency for listening. Both people can talk on the call at once. The genius of the cellular system is the division of the city into small cells. Cells are normally thought of as hexagons on a big hexagonal grid. This allows extensive frequency reuse across the city, so that millions of people can use cell phones simultaneously. So, what happens when someone calls you? When you first power up the phone, it listens for an SID on the control channel. The SID is the System Identification Code, a unique 5-digit number that is assigned to each carrier by the Federal Communications Commission. If the phone cannot find any control channels to listen to, it knows it is out of range and displays a no service message. When it receives the SID, the phone compares it to the SID programmed into the phone. If the SIDs match, the phone knows that the cell is communicating with this part of its home system. Along with the SID, the phone also transmits a registration request. The MTSO, also known as the Mobile Telephone Switching Office, keeps track of your phone's location in a database. The MTSO picks a frequency pair that your phone will use and the cell that will take the call. And once your phone and the tower switch on those frequencies, the call is connected. Now you are talking by a two-way radio with a friend. Cell phone technology has advanced tremendously in the past 20 years. It kind of makes you wonder what the mobile industry has to offer within the many years to come. Digital wireless technology.
So I was watching a movie this past weekend and I saw this guy carrying one of these. And I remember thinking, wow, that is so cool. I mean, pretty soon it's going to be like flip phones from the flip communicators from Star Trek. Little did I realize that, man, we were going to blow through that technology as well. So now when you're watching Star Trek, you're going, that's it? That's how they're communicating? Well, yeah, but at least they're communicating with people out in space. That has to be a little impressive, right? Okay, so any questions about cell phones? Now you understand where cell phones come from, right? The cell. And you know they're creating another cell over there behind Kmart. Did you notice that? There's a new tower going on there. Yeah. Okay, so let's continue taking a tour. Now we're going to focus on visible light and the visible light range. How light bulbs work. I've always found this to be interesting.
Contrary to popular belief, the original light bulb was not invented by Thomas Edison, but Sir Humphrey Davy in 1809. Creating the first electricity-powered light, the invention was greatly refined 60 years later by Edison, designing a powerful bulb that could burn for up to 40 hours. This was the first incandescent light bulb. To understand it, we first have to recognize light at an atomic level. At its most basic form, light is seen as a series of particles called photons. They are created as excess energy packets when an atom's electrons suddenly gain and lose energy. When an atom is energized, its electrons shift further away from its core. When the energy stops, the electron returns to its natural orbit, releasing built-up energy as a photon. By repeatedly energizing atoms, it's possible to generate a steady stream of light energy. In a light bulb, the energy source needed to energize the atoms is provided via electricity traveling through its base, electricity simply being the movement of free electrons. The key component that made Edison's design so groundbreaking was the filament at its center. Being the most important part of a light bulb, it's the size of the filament that determines the intensity of the light emitted. In an everyday bulb, the filament is about 50 centimeters long, but is coiled down to a smaller size, then coiled again, leaving a 2 to 3 centimeter piece in its place. Tungsten is usually chosen for its extremely high melting point. Electrons burst through the filament, but because it's so tightly coiled, they'll frequently fly off and bump into each other, causing the filament to light up and become extremely hot. All this takes place inside an airtight bulb. If the reaction were to take place in open air, the heat generated would be enough to ignite the surrounding oxygen, destroying the filament. However, in a vacuum, when the filament is heated, the vibrating tungsten atoms occasionally break off. If enough do this, the filament splits and the light bulb is broken. To counter this, the empty bulb is packed full of an inert gas such as argon or krypton. With the gas, any atoms that break off bounce off the gas atoms and rejoin the filament, effectively quadrupling the bulb's life. Although incandescent light bulbs are a staple of modern technology, they've been proven to be very inefficient. An everyday light bulb produces about 20% visible light, with 5% released as light outside our visible spectrum, such as ultraviolet and infrared. The rest is produced as heat, leaving the bulb red hot. To counteract this, the fluorescent light was invented. Using an entirely different process, it's 5 times as efficient at producing light. This will be discussed in a later episode. There are 3 main components to an
Okay, so incandescent light bulbs are just brilliant, as you can see there. Any questions about how an incandescent light bulb works? Somebody asked me today, well, what's an inert gas? Well, it's just a gas that doesn't react with things, like noble gases. If you were to put oxygen or nitrogen in there, it would react with the metal, and it would break the metal. It would change the consistency of the metal. Now, thanks to global warming and our proponents of global warming in Congress, they have banned the incandescent light bulb because it is so inefficient. And it is very inefficient the way we're designed. We can also design them in a way that they're far more efficient, but they would be more expensive. Okay? So little by little, they're phasing them out. But I have been buying them up. So pretty soon, what they're going to discover is that these little curly Q, the fluorescent light bulbs, are dangerous, and people will want to get incandescent back. And guess who will have them? Me. I will be there at the park with my trench coat and my hat and my sunglasses, walking around waiting for people to come up and say, hey, do you have a 75? Yes, I have a 75. And I'll open up my trench coat and show them my inventory. So I'll be making lots and lots of money while you guys are just sitting around in the dark. So, of course, if a cop gets you, you got to be careful, because you got to run with all these light bulbs jingling around you, and if you fall,
Or if he tackles you.
yeah, if he tackles you, that could be, ooh. Okay, so why are the little curlicues potentially dangerous? Keeping in mind that if you read the fine print, you'll find out that if you break the curlicue, you should evacuate your house of all people and pets, and then call the hazmat team. That's kind of scary. No, it has a tiny little bit of mercury. These fluorescent light bulbs are the same thing, but they're just made in a smaller version. So let me explain to you how the fluorescent light bulb works. Do you have a question, Alec?
The basic principle of operation in a fluorescent lamp is simple. You have a glass tube, and inside, all you have in the tube at each end are electrodes called cathodes. And in the case of the hot cathode, they're like a little filament. That's why you have two pins on each end, because each pin goes to one end of the filament. And these filaments inside are electrodes that send current through the gas in the lamp. The gas in the lamp is argon, and there's a little bit of mercury in the tube, just a tiny amount, like just a pinhead amount of mercury. And how it works is when the current is switched on, these cathodes heat up, and they're coated with a special material that gives off electrons. It works on the same principle as a vacuum tube, and it's called thermionic emission. When it heats up, it gives off electrons. And that's good, because when the filaments heat up, they give off the electrons. Then a high voltage pulse is sent through the lamp from the starter, and that pushes those electrons through the lamp from one end to the other, and it starts an arc through the lamp, through the gas that's in the lamp, which is argon. And this argon arc makes enough heat to vaporize the mercury that's in the tube, and that goes into the arc stream and produces ultraviolet radiation.
Okay, that should make you nervous right there. Because the argon, once it gets excited, the electrons in argon, once it gets excited with the electricity that's going through it, is going to give off light that you can't see. It's UV light. And that's also harmful light. So this is what they use in order to kill germs. Okay? You've seen that in the barber shop or maybe the beauty shop. They'll put it in these special apparatus that there's a light coming from them. Okay, that'll kill them with germs. The same thing would happen to us. So what they do is they coat the inside of these light bulbs with this material called phosphor. And what phosphor will do is absorb the UV light and then give it back out in visible light, white light. So that's why you're seeing white light coming out of there. Okay, because of the phosphor. Yes? Technically, probably.
So instead of pulling the fire alarm,
Yeah, just shatter one.
just then you won't be. Guys, that's how they see
Don't.
it. Yeah.
I doubt that they'll evacuate the whole building for that. All right, let's continue.
And ultraviolet light. And the ultraviolet light hits a powder on the inside of the tube. That's why they're white. It's called a phosphor. And it's a material that glows when ultraviolet radiation strikes it. So when the UV radiation produced by the arc through the gas in the lamp hits the phosphor, it makes it glow, and that's what produces light.
All right. Any questions about phosphorescence? Phosphorescent lamps. Okay, those are the two ways in which they can produce visible light. All right, let's talk about red alert. That's one of my favorite stories. Yes? LEDs, I don't quite understand how they work, but no, they're different. And they're much safer. They produce very little heat. and they will last a whole lot longer. I am slowly but surely converting all my house light bulbs into LEDs.
So will we eventually learn about those? Or is that just like...
It doesn't produce light in a way that is consistent with what we're studying. So I'll try to look for it. That sounds interesting. I'm also interested in how LEDs work. But they're really expensive. They're about $10 a bulb. But when you consider that you'll run through 3 or 4 of the curlicues and 8 or 9 of the incandescent in its lifetime, it more than pays for it. Yes? Well, what you're using there is, we'll talk about it when we talk about spectroscopy. Okay, we'll get to it. All right, red alert. What does red alert have anything to do with it? Back in the turn of last century, when they started installing electricity in ships, in warships, they realized that now, if you were in a war situation, you could actually see the enemy for miles and miles away. Why? Because when white light travels, it will travel for many, many miles, because it has blues and greens and yellows in it. Okay? So they realized, hey, we're giving away our position if we use electricity. But by then they had designed the ship so that the bridge was inside, and you could not actually run the bridge without electricity. So what they decided to do is have a different lighting system when they were in a battle situation. They would call for red alert, and they would dim all the white lights and turn on the lights with a coating on it that would only release red light. So that gave them enough energy to be able to see their instruments, but the red light simply does not travel as far as the white light. So that wouldn't give away their location. So radar came in, and we no longer have spotters looking for other ships' lights, okay? We can find them with our radar. We can find them now with our satellites. But they still use red alert. They'll still dim the lights. They'll still turn on red lights. Now it's more psychological, because at this time, we realize that when you turn on red lights, it agitates people and makes them nervous. And you want sailors to be agitated and nervous when you are in a battle situation. You don't want sailors to be bored and ready to fall asleep. Now, what about Star Trek, you Trekkies? What happens when they're in a battle situation?
Well, normally the lights just all shut off.
Yes. So here in the far future, there's definitely no reason to do that, and yet they still do, because it's what we expect. What about photography? We've talked about photography, the use of red light, right? And tanning salons, they use those light bulbs without the phosphorescent coating. They will be releasing ultraviolet. Folks, that's damaging your skin. That's damaging your skin. In small amounts, if you have enough melanin, it does help. But in large amounts, it will damage your skin. All right, so a little bit of electromagnetism, the flavors of light. Got it? There's so much we could say, so much we could talk about. We just don't have the time.